Now we're going to look into something called technical safety, which is safety implemented using electronic equipment, PLCs, or other automation devices. So again, we're going to look into the compendium. And here we have technical safety is here. And mainly we're going to look at the figures again, but here is something about a HACCP and HACCP ID. We have to determine is it dangerous, this process dangerous, can it cause damage to personnel, equipment, environment, and so on. And it has something to do, talks a little about risk, what risk is, and here's an example. Risk is described use frequency of the hazardous condition, exposure, time, and possibility for it to happen, as an example. Security and gas leaks due to overpressure versus overpressure once every year, and the safety system phase every 10 times. Consequence is that gas leaks might occur in the system due to overpressure every 10th year, which again might be unacceptable. So this is all about barriers. There's some requirements for the barriers. They have to work all the time. Specify the requirements. Compromise barriers must be compensated for. So it has to do about risk reduction. If we have get inherent risk or natural risk here, we have to do some measures to get down to acceptable risk. So what we have external risk reduction can be mechanical stuff and so on, but then we have the safety instrumented system, which is technical safety. And then we have other risk reduction technology. So here is acceptable risk, total risk reduction, and then we have a residual risk. And it's never zero risk in a system. Something can cause something to happen in a system. And then here we're looking at the barriers. And here is the onion. So we have a process control system in the center with alarms. And the operator, he kind of get alarms, handle the alarms, acknowledge the alarms, he's seen them, and mitigate the problem, or try to mitigate the problem. Then we have a process shutdown. On the outside, shut down parts of the process with problems. And then we have another layer, which is called emergency shutdown system, ESD system, which shuts down a lot of parts of the process or the entire process. ESD 0. Everything has been shut down. And then also here for technical safety, especially in Norway, this is if you have mechanical barriers. It's blow-down valves and stuff like that, overpressure valves as the outer layer. And if, let's say, without mechanical barriers, you will not get any approved safety system in Norway. So this is called a safety instrumented system, all of this, not the mechanical barriers, of course. And there is a norm, the IEC norm, that is specifying requirements for this kind of safety. And it works on probability for failure on demand. Let's say there is a safety system sitting there, has to do something, how often can it fail? So for SIL 1, for instance, it can fail 10 out of 100 times when it's required to do something. But remember, it can fail the first time it has to do something, not the 99th time. So it can fail the first time. You never know. And the reason why here is these are the error or fault categories. Safe undetected, no problem. Safe detected, let's say no safe safe undetected, or the safe detected is not a problem, it's green. Safe undetected, but it's not dangerous. And we have bring this safe undetected to safe detected with operational philosophy, self-test in the system, and so on. Then we have dangerous, and they are detected. So we know about them. They're dangerous errors, but we detect them, but we can operate it to safe detected. And then we have what's left, dangerous, undetected. They're dangerous, we don't know about it. That's the reason why it can fail the first time, because there is an error in the system, it's dangerous, and we don't know about it. But we have fail-safe construction, we have, it's basically fail-safe construction we have to mitigate things like that. And here is a safety loop, and the safety loop is from the detector through the safety instrumented system, the actuator, and whatever it does. So the SIL has to do with all of these. And this is the SIL level, safety integrity level, is pure statistics. This is all statistics. So the weakest link here determines the SIL level that you have for the system. And then if we look into the electronics, this is a safety instrumented system. We have pressure, transmitter, transducer or something, and a valve. So it's going to do something. And there's going to be requirements on the valve too. So there is data on the valve and the sensor itself. But then it's the electronics, the logic solver that is often called. It has a CPU. It has input modules. It has output modules. For the input modules, there is a microcontroller, has an analog to digital converter, digital to analog converter, and so on. So it outputs a value, reads it back. It's nice, preferably as close to the pressure transmitter as possible. So it's fine. It's a known value. We read it back. My input module is intact. Same with output module. Output has a small current, so that the valve doesn't do something if it's been closed, or that it so it doesn't close if it's open, whatever. So a small signal or a signal out there, or if it's kept open, we just read back our signal here and say, okay, what I have output is what I have, so this is okay. So this is a self-test. And the CPU itself has a watchdog. So if your program doesn't reset some watchdogs at regular intervals, which means the program has stopped doing its task, a watchdog is triggered. Usually the CPU just shuts down and the entire system shuts down, valves open, or if they fail, valve closes. If they fail open, they open, whatever should do here. If it's emergency cooling, for instance, by head in a tank or something, the valve would open. So then we have cooling, if this system is doing cooling. Okay. And then a safety instrumented system is a programmable system, so we have to develop software. Here is the process, which is taken from some guidelines, Norwegian guidelines from 2004, but it's valid. So we do specification, application, specification, design, development, module development, code. So this is specification. We have to do some coding. Then we test the module. If they fail, we have to go back to the development and specification and do code development, revise the code development, application software testing, which is testing modules, interaction, and so on. If it fails, go back, do it over again. Integration testing, we test the entire application. If here are some faults, something, go back to scratch, do it all over again. And then we have the safety validation, which means that the safety integrated system has been installed, it's validated and tested. If this fails, of course, there's something wrong with your safety requirement specification that you did in your HACCP, and has had it move back to scratch, go through it again. So this is costly. Don't do errors here, because it's going to cost you here quite a bit of money. And then there is a ISO norm 2 for safety. That has to do with machinery. We are not going to go through this in detail, but there is let's say, directive that's used in the EU area for the machinery directive. Leads to a CE labeling of your equipment. So what you should do here, risk assessment is important, and this reduce risk by design. This required safety measure identified and assigned to performance requirements. Here we don't have SIL levels, we have performance requirements A, B, C, D, and E, I think, or something like that. And you have to demonstrate that the safety features or functions that you have provided for gives you an acceptable residual risk, and so on. So that was technical safety. So here we look at technical safety, and technical safety is safe access by a safety instrumented system of some sort, a safety PLC with instrumentation, inputs and outputs, sensors, actuators, and then the requirements. Here we looked a little on safety integrity levels. We looked at just the SIL 1, where the system is allowed to fail 1 out of 10 to 100 times, but it can fail the first time it should do something, which in some plants, let's say nuclear facility, is not too bad. They would be SIL 4 or even better, fail 1 out of 10,000 times or 100,000 times, but it could fail the first time still, because this is all statistics. Be aware of that.